Very much. Thank you very much. It's wonderful to be here and to be still able to come and give talks 3 weeks in. So today's topic is dissipation in neutron star mergers. So let's get going on that. So as I mentioned before in earlier talks, the observed phase diagram of QCD is a bit sparse. So we have done heavy ion collisions, and we see the hadronic phase crossing over to the quark-gluon plasma phase. We have neutron stars where we can see a nuclear superfluid and a superconductor. And the new arrival on this scene is neutron star mergers, which we hope will give us insight into warmer forms of matter at nuclear density and above. And one of the reasons we're excited about this is that there is potentially interesting phase structure there. So this shows what we imagine might be there, a critical line ending at a critical point, chiral critical point, a color flavor locked phase up at high densities. And in between, we don't know what, something, maybe some kind of quark matter. And our hope is that neutron star mergers will provide us with information about the possibly interesting phases of matter in this region. So, okay, how is this going to work? Well, what we hope is that observers will see signals from neutron star mergers. One of the ones that we've heard about recently is gravitational wave signatures like this one that's shown here. And that comes from the in-spiral, the merger when the neutron stars combine, and the ring down afterwards. And in order to get useful information about the phases of dense matter from these sort of observations, we need to perform simulations. We do gravitational physics simulations of the merger of two neutron stars. And those need to incorporate the relevant microscopic physics. So what I'm going to be talking about today is the sort of microscopic physics that goes into these sort of simulations. What do we need to include? So this is something that I'm sure all of you have seen. The kind of data that we have so far, our best event was in 2017. This nice chirp here where we saw the in-spiral and right up to almost the merger. And we're hoping, we're doing all this work, the simulation people are doing their simulations of mergers, and we as microscopic physicists are trying to give them the relevant properties of the matter to include in their simulations in the hope that future detectors, like the Einstein telescope or Cosmic Explorer, will hear more of the in-spiral and will get the merger and the ring down, and that we may be able to use that data to tell us something about what forms of matter there are in neutron stars, and are there some interesting phases like we saw in the quark matter conjectured phase diagram. But so for right now, the work we need to do is help the simulations to be accurate by providing them with the relevant microscopic properties of the matter. So here's an outline, that's the context. So here's an outline of the talk given that context. We think of neutron star mergers like experiments. They probe the properties of dense matter, which is what we're interested in. If you go to talks about this, very often the pride of place will be held by the equation of state. You'll hear people talking about the equation of state a lot. So my goal in the talk today is almost not to mention the equation of state. I want to talk about other things that people don't talk about so much, such as out of equilibrium phenomena. And the main one I'll talk about is the flavor being driven out of equilibrium. And as we'll discuss, that leads to bulk viscosity. Other things that one could talk about that could be relevant is when the system is out of thermal equilibrium. There may be hot regions and cool regions, and heat then flows from the hot regions to the cool regions as it tries to equilibrate, and that gets you to thermal conductivity. And there may be something similar with the flow. If you have regions flowing past other regions going faster, then shear viscosity is another out of equilibrium phenomenon, transport phenomenon, that tells you how quickly those regions all get the same fluid velocity. And the real point here is that these out of equilibrium or equilibration phenomena are more useful than the equation of state if you're interested in the phase structure. And you know this from terrestrial condensed matter physics. If some condensed matter physicist has a new material and they want to know what kind of material it is it a conductor or an insulator? Is it a superfluid? Is it a superconductor? They're not going to measure its equation of state. You know, the equation of state of superconducting mercury is not that different from the equation of state of normal mercury. What's different is how it responds when it's driven out of equilibrium by having an electric field applied to it or having a magnetic field applied to it. So it's really very often these transport type properties or equilibration type properties that are qualitatively different between different phases. And the equation of state is interesting and important, but it's not the best way of discriminating between different phases.
Excuse me. So
yes.
These out of equilibrium phenomena should also, of course, like depend on equation of state.
Yes, there'll be some equation of state dependence in them.
Okay. Mm-hmm.
But they'll generally have something else that they depend on, some sort of mean free path or some sort of rate, and that's what we'll be talking about in the lecture today.
What is the definition of the phase if it's not equilibrium? So
well, it's the properties of the phase. It's how it responds to being driven out of equilibrium. Okay, so like a superconductor, right? How you detect it.
Linear response.
Yeah, well, so it could be linear. I'll be talking about linear response today, but actually it needn't be linear response. I mean, linear response is how people normally do it, but you could go beyond linear. There's nothing stopping you. Then it's not so simple as just viscosities and conductivities. Those are defined in linear response. That's true. Okay, so the thing I'm going to talk about is flavor equilibration, which is, in the case of ordinary nuclear matter, it's equilibration of the proton fraction. So I'll talk about the relaxation time for the proton fraction, how quickly the proton fraction goes back to its equilibrium value if it's pushed away from it. And in particular, I'll talk about this concept of critical equilibration when this relaxation is playing an important role. And the physical manifestations of that I'll talk about today are things like bulk viscosity, which leads to damping, or what one might call sound attenuation, which just means the damping of density oscillations. So those are the things we'll be talking about. All right, so let's talk about density oscillations. Are there density oscillations in neutron star mergers? Well, we look at simulations. Here is data from a simulation done by the Frankfurt group. Along the bottom here is time in milliseconds. So we're seeing the first 20 milliseconds or so after the neutron stars merge. And these individual lines here are showing the density. That's the density up the vertical axis in units of saturation density. They're showing the density of individual fluid elements. So the simulators here just chose some fluid elements and tracked them through time as they experience this violent event that the neutron star they were in, that was sitting quietly, minding its own business with not much going on, suddenly gets smashed by another neutron star, and these fluid elements now experience some violent events. And what do they experience? Well, you see they experience these very strong density oscillations. In the first few milliseconds, it's definitely not linear response, right? It's amplitude fluctuations of 50% or more. And then after a while, it settles down to more moderate density oscillations. But the key points here are, firstly, there are density oscillations. So it's worthwhile talking about what sort of out of equilibrium phenomena might be created by those. And secondly, what are the properties here? The amplitude could be quite big, and the period we see is in the 1 to 2 millisecond range. So we're talking about frequencies around a kilohertz. And that's not a surprise. In general, neutron star oscillations all tend to be in the kilohertz range for reasons to do with how big a neutron star is and the speed of sound. Basically, you divide those and you get things that tend to be in the 1 to 10, so 1 millisecond plus or minus a factor of 10 either way.
What is the color difference?
There's just different fluid elements that they chose to watch. A little cell. An element means a cell, a little piece of fluid, yes. And they then track it. And as it moves around, it gets squeezed and unsqueezed, you know, and that's what you're seeing here, that the fluid elements experience these density oscillations.
I just want to check. So this is the result from the ideal hydrodynamics.
Yes, there's no dissipation. The small print is here. Flavor equilibration has been neglected here. There's no inbuilt dissipation in this.
So the oscillation is like purely from this in spiral. I mean
yes, it's the violent flows going on in the merger. It's actually as these fluid elements get pushed down and up, and they compress when they get pushed down, and they expand when they get pulled up. That's what's going on there. So
Just for clarification, how should I imagine these simulations on fluid dynamics with a gravitational?
Yes, it's two balls of nuclear matter attracted under gravity, orbiting around each other, spiraling in because they emit gravitational waves and lose angular momentum, and eventually merging. And
that the nuclear matter is also self-interacting.
Yes, right. It has an equation of state. And the question is here, what I'm going to be looking at is what other properties apart from the equation of state are relevant. And in this case, I'm going to be talking about properties related to density oscillations and what I'm calling flavor equilibrium, which, as I said, really means the proton fraction, which I'm going to describe all of this in great detail. That's the topic of the talk. Any other good questions to help us set the mission?
What's the final state?
The final state? In this particular simulation, well, we're only looking at the first 25 milliseconds. I don't know if this particular merger ended up collapsing into a black hole, or if it made a hypermassive neutron star, or, I don't know what happened. Generally, these density oscillations die away once the thing settles into a new spherical shape and eventually, settles down. So the questions I'm going to be asking here are, do these density oscillations drive the system out of flavor equilibrium? And does the system trying to get back into flavor equilibrium in turn affect those oscillations?
Is there a question in Zoom audience?
It may just be an unmuted microphone.
Yeah, all right. And also there's a question from Motoi. So what if one of two balls is a black hole?
Okay.
Like neutron star?
Yeah, so you could look at a neutron star black hole merger, and then I'm not sure the in-spiral part of that would look similar, right? Before they touch, they don't really know. And there may be interesting, this plot doesn't tell you what's going on in the in-spiral, but the in-spiral may separately have its own density oscillations induced by tidal forces. The merger itself of a black hole and a neutron star, I have to admit, I don't know that much about it, but I think it tends to just be that the black hole eats the neutron star, and there isn't as much interesting gravitational wave production. But I might be wrong about that, so I don't want to prejudice anyone against those types of mergers. Okay, so this is the question, right? Density oscillation. Yes.
Sorry, may I ask a question?
Yes.
So here you are just talking about the density, time evolution of the density, and it does not involve the flavor currently.
Thank you. That's my next slide.
Okay.
Okay, so good question, and that's what I'll be getting to right now. Okay, so let me do that. Yeah, the different colors are different fluid elements. I think I answered that. Okay, so let's talk about how flavor comes into the story. So first, let's make sure we know what we're talking about. What is this nuclear matter fluid whose properties we're studying? Well, as many of you know, a typical fluid element here is mostly neutrons with a small fraction of protons and an equal number of electrons, because it has to be electrically neutral, and maybe some neutrinos, which are generally less likely to be thermally equilibrated. The other particles are thermally equilibrated because they experience strong or at least electromagnetic interactions.
The temperature is less than maybe a QMEB, right, in this case?
Yes, so in mergers, the temperature can be up to 50 or even 80 MeV. But
you write not thermally equilibrium, so
right, it depends on the temperature.
Yeah, of course. So
yeah, it depends on the temperature. So they may or may not be thermally equilibrated. It depends on the temperature, as you said. So that means your fluid is described by your fluid element that doesn't need that many parameters to describe it because it's mostly in equilibrium. So there's the density, the baryon density, protons plus neutrons. There's the temperature. there's the proton fraction, what fraction of the baryons are protons, and if the neutrinos are trapped, then there's a lepton fraction you can talk about as well. Those are the conserved quantities or the things related to conserved quantities that you can talk about. So it's not that hard. And so the equation of state, the thing that everyone talks about, is what is the pressure as a function of these state variables? What's the pressure as a function of density, temperature, proton fraction, maybe lepton fraction? All right, so this is our fluid. We're going to compress it. Now, what happens when we compress it? So each fluid element has a sort of favorite or a favorite proton fraction. Each density really has a certain proton fraction that the system will relax to. So here we've got a plot of this. So here's the density in units of saturation density. This is for the IUF equation of state, one of the standard relativistic mean field models people use. This is the proton fraction up the side here. So at saturation density, the proton fraction is about 5%. 5% of the baryons are protons. As you go up, the proton fraction rises. At 3 times saturation density, it's about 10%, and so on. And here, when it gets to 11%, is this thing called the Direct-Erker threshold, which we may touch on a little bit, but it's not essential for our purposes. So what this blue line here, which tells you what's the equilibrium proton fraction at each density, it's determined by properties of the strong interaction, the nuclear symmetry energy, things like that. How many protons does it want to have? And the requirement of electrical neutrality, which says that the system has to be electrically neutral. And how does it get to this equilibrium proton fraction? Well, it doesn't happen. So imagine you've got your little fluid element that starts off at, twice saturation density, where its proton fraction is about 8%. And then you saw those oscillations earlier on. It gets compressed. Suppose it gets compressed to 3 times nuclear saturation density. Now its proton fraction wants to go up to 10%. So it wants to turn some of its neutrons into protons. But this is not an instantaneous thing because it requires a weak interaction, right? Only the weak interaction can change protons into neutrons and vice versa. And the weak interaction is slower, much slower than the other interactions. So we have to ask ourselves, how quickly can this happen? So the idea is that density oscillations can drive the system away from the equilibrium proton fraction here. They drive it off this blue line, and that has different names. People call it beta equilibrium or beta equilibration, chemical equilibration, isospin equilibration, flavor equilibration. These are all names for the same thing, getting the proton fraction back to its equilibrium value after you've compressed or uncompressed a fluid element such that it's no longer at the equilibrium value. So that's how flavor comes in. So let's look at this situation. Okay, let's write down a couple of very simple equations that would describe it. So here's our fluid element, and we give it some average density here, and we give it an oscillation in its density, an amplitude delta n, and some angular frequency omega. So its density has this little cos omega t correction where it's being compressed and uncompressed at this frequency omega. And we also put in the process that brings the proton fraction to its equilibrium value for whatever the current density is. So whatever the equilibrium value is at the current density, this equation here says the proton fraction at some rate, we call this the relaxation rate. So at some rate gamma, which itself depends on density and temperature, at some rate, the proton fraction is trying to relax back towards its equilibrium value. Okay, so we've got an imposed density oscillation in this equation, and we've got a relaxation equation for the proton fraction with some rate. So we've got 2 timescales in this problem. We've got the frequency of the oscillation, how rapidly are we compressing and uncompressing the fluid element, and we've got a property of the fluid element built into it, which is how quickly does its proton fraction relax back to the equilibrium value. Okay, so very simple setup, just 2 timescales that we can compare. So let's look at some different limits, right? We know what to do. We're physicists. We know what to do when we're given 2 timescales. We look at different regimes according to which one is bigger. So let's do that. So here, let's look at fast equilibration. Supposing that this equilibration rate is rapid compared to the frequency of the applied oscillation. So here is a schematic version of that plot I had before. Baryon density along the bottom, proton fraction up the side. The equilibrium is this blue line. If the equilibration is fast, then when you subject this fluid element to an externally imposed density oscillation, this delta n cos omega t, what path is the fluid element going to follow on this diagram? Well, I think you can probably guess it's going to go back and forth along the equilibrium line, right? Because gamma is fast, relaxation is fast. So when you compress it, it instantly re-equilibrates. So it always lives on the equilibrium line. So that's fairly straightforward, okay? What about if the equilibration is slow? Okay, suppose it takes a long time, much longer than one period of the oscillation for this, for the proton fraction to get to its equilibrium value. Then what trajectory do we expect the fluid element to follow in this diagram? Anybody in the room here with me want to guess? What is it going to do if the okay, I see, you know, I see it gestures like this. So very good, right? The proton fraction stays the same, right? You compress it, it starts off 7% protons, you compress it, there isn't time for any protons to change into neutrons, so it's still 7% protons, right? The density has gone up, but the percent hasn't changed because we haven't changed the identity of any of the particles. So in both these cases, you don't actually need to solve this relaxation equation, right? The equation of state or the initial conditions tell you what the proton fraction is going to be. In this case, it just always sits on the equilibrium line. In the slow equilibration case, once you know the initial proton fraction, that's it. Okay, you don't need to solve the equilibration equation, the relaxation equation, in either of these two limits. Okay, so what's left for me to talk about, right? What about what happens when the relaxation rate is comparable to the frequency of the applied density oscillation? So let's look at that. Okay, so this is what I'm calling critical equilibration. So now, what trajectory is the fluid element going to follow in this diagram of density and proton fraction if its relaxation rate is comparable to the applied density frequency, oscillation frequency? Anybody want to make this guess? Nobody. You think it goes in some sort of, I see how, okay, I'll see the hand going in a second. Okay, so it's going to look something like this. All right, it's going to go, you compress it, the density goes up, you uncompress it, the density goes down again, but it's not going back and forth along one line. And the critical point here is that if I tell you the density of a fluid element, you cannot tell me the proton fraction right away because it depends on the recent history of the fluid element. It depends, was it recently compressed and it's now being uncompressed? Was it recently uncompressed and it's now being compressed? The thing has a little bit of memory because the relaxation of the proton fraction is happening on the same time scale as the applied density oscillation. So when you're in this regime where the relaxation rate of some quantity, in this case the proton fraction, is comparable to the time scale of the applied sort of deviation from equilibrium, if those are comparable, then you have to include this relaxation equation in the fluid dynamics. So you can track each fluid element and work out what its proton fraction is at each moment based on what it's doing now and its recent history. So now, what the rest of this talk is going to focus on is some other features of critical equilibration, which is phase lag between the density and the proton fraction, which is what you're seeing here, that they're out of phase with each other, which is why you get a circle. This is a Lissajous figure, right? And how that's related to things like bulk viscosity and damping. This will back react on the density oscillation and damp it. And we're going to explore that physics for the rest of this talk. But firstly, let's just answer, is there critical equilibration in mergers? Do we actually get this situation where the applied frequency, the frequency of the applied density oscillation is comparable to the innate property of the material, which is how fast it can equilibrate its proton fraction? Are those timescales similar? So, well, we know, remember we saw in that simulation data that the typical frequency for a density oscillation is about 1 kilohertz. So the angular frequency is about 2 pi times 1 kilohertz. So we got that number. We need to get the other number. We need to calculate how quickly does the proton fraction relax in nuclear matter. And that is determined by the weak interaction, because that's the only interaction that can do this. In particular, what are called Urca processes, in which neutrinos play a role. So it's actually quite difficult in general. There are 2 limiting cases where we can calculate the relaxation rate. It's a question of whether the neutrinos have a very long mean free path, and so they escape, and you can consider the material as being transparent to neutrinos, or in the other limit, the neutrinos have a very short mean free path, and they're trapped, and they form another equilibrated gas like the electrons and the protons and the neutrons. So in those limiting cases, we can calculate it. In between, it's ugly and horrible. So in the neutrino transparent regime, what are the processes that restore the proton fraction to its equilibrium value? Well, they are neutron decay, which we all know. Neutron decays to proton, electron, and antineutrino. And electron capture, proton captures an electron and turns into a neutron and a neutrino. The point in this case is, since the material is neutrino transparent, there are no neutrinos in initial states. So neutrinos are radiated away, but there are no processes where a neutrino is in the initial state. In the neutrino trapped case, it's dominated by the forward and backward versions of the same process. This is the 2-into-2 process in this case, where neutrino plus neutron turns to proton plus electron, or vice versa. And you can also have the backwards version of neutron decay as well. In this case, when it's neutrino trapped, you do get neutrinos and antineutrinos in initial states. So we can do the calculation in these simple limiting cases. So if we do that, what do we get? Do we find that this relaxation rate, which depends on density and temperature, can be sometimes comparable to the kilohertz timescale of density oscillations induced by mergers? And since it depends on density and temperature, the real question is, at what densities and what temperatures is the rate comparable to the oscillation? And do we get those densities and temperatures in mergers? Does the question make sense to everybody? Get the idea?
Yeah, you consider the neutron star merger case where the frequency is high. But for example, can we consider, for example, in the neutron star cooling phase?
Yeah.
Is that possible?
Yes, you can. So you can talk about. So I'm focusing on mergers, just because kind of they're the new thing. But yes, people have done calculations like this for oscillations in individual neutron stars. There are oscillations like R modes that are unstable and can develop on their own, and those produce density fluctuations. And the same thing, they drive the proton fraction away from equilibrium. So you could be talking about an individual neutron star whose temperature is in maybe the 100 keV range, right? Or you could be talking about a merger where it could be in the 100 MeV range, right? So there's a range.
Yeah, if this could occur in cooling phase, then maybe there are both 2 cases of the rapid cooling phase and the slow cooling phase.
Right. That's to do with the direct Urca threshold.
Yeah, maybe that's here.
Right. But in this case, we're interested in density oscillations, but there's also, one could look at other things like thermal conductivity. But for right now, just in order to have one thing to talk about, we're focusing on density oscillations. So I'm just going to cut to the answer. Okay, I'm just going to show you the answer to this question, and then we'll go from there. So here is a plot of the proton relaxation time. I've converted it from a rate to a time. And this is in the same, we're going to do these sort of plots over and over again in this talk. Density along the bottom in units of saturation density, temperature up the side in MeV. And this right-hand plot is from the neutrino trapped regime, and this left-hand plot is the neutrino transparent regime. They're covering the same range of temperatures. Really, transparent is lower temperatures and trapped is higher temperatures, but I just want to make it easy to compare. So what we see is some straightforward conclusions. So we see that as you increase the temperature, the relaxation rate gets faster. Here in the neutrino trapped regime, it goes from 10 to the minus 4 milliseconds, 10 to the minus 5, 3 times 10 to the minus 6. You increase the temperature, the proton fraction relaxes faster. The same is true over here in the neutrino transparent regime. The relaxation time is, in this case, at about 2 MeV, 100 milliseconds. Then you turn up the temperature, you get 1 millisecond, 0.1 milliseconds, 0.01 milliseconds. So as you heat it up, it relaxes faster. The contours are pretty horizontal though, right? The density is not making so much of a difference. It's mainly temperature that's driving how quickly the thing relaxes. And that's because these processes, those Zerker processes, involve particles near the Fermi surface. And as you turn up the temperature, there's more available states near the Fermi surface. There's more holes below the Fermi surface. There's more particles above the Fermi surface that can participate in these Zerker processes. So these Zerker processes tend to have rates that go like powers of the temperature, T to the 5th, T to the 6th, that kind of thing. And so that's what you see here. You see as you increase the temperature, the relaxation gets faster. The system can equilibrate its proton fraction faster. And if you look at compare the two plots, neutrino trapped regime versus neutrino transparent regime, you see that in neutrino trapped matter, the relaxation is really very fast. It's a fraction of a millisecond. In the neutrino transparent regime, on the other hand, you see we get relaxation timescales, 25 milliseconds, 1 millisecond, that are comparable to the timescales that we saw for those oscillations. Okay, they're comparable to that oscillation frequency. So this thick contour here in the middle of the transparent regime, that's showing you critical equilibration. That's showing you where the relaxation time is comparable to that 1 kilohertz, the angular frequency or the inverse angular frequency for that 1 kilohertz oscillation. So this thick line here, which sits at a temperature of about 4 or 5 MeV, is saying here you're going to get that match between the equilibration timescale of the material at that temperature is going to match the 1 kilohertz timescale of the typical density oscillation that you get in a merger. So indeed, critical equilibration is happening in mergers if they reach these temperatures of 4 or 5 MeV, which some parts of them do.
So excuse me. So it seems like relaxation time is like varying exponentially rather than like power. Is it really a power?
It is a power, yeah. I mean, okay, it is a power. That's all I can say.
So the power is large.
It is a high power, yes. Yeah. Okay.
May I ask a question?
Yes.
According to the neutron star cooling model, what is the time scale that what is the time span that the two time scale are comparable?
Well, so this is a merger, right?
Yes.
I'm talking about
okay, sorry. I see. So I see. Sorry, I misunderstand.
Okay, yeah. So in a merger, everything's happening on a much faster time scale. It's milliseconds, 10 milliseconds. Those are the time scales we're talking about in a merger. If a neutron star is cooling, it's a longer time scale. And one could talk about that, as I said earlier, you could talk about oscillation modes of individual neutron stars, R modes, and things like that being damped and experiencing this sort of out of equilibrium behavior. But also, the frequency of typical oscillation modes of neutron stars is also kilohertz. But okay, let's stick to mergers just because I want to, not make my life too complicated. But you're quite right to say that it doesn't have to only be mergers. Okay, so
may I ask a technical question? So,
yeah.
So here you are considering the two limiting case, and I guess that the neutron trapped regime is captured by assuming that the system is thermally equilibrated and including the neutrino sector.
Well, but they can be driven out of equilibrium when you compress, right? But yes, it will return to an equilibrium in which the neutrinos are an equilibrated gas. That's what it relaxes to.
And how can you describe the neutrino transparent regime using such a kind of a thermal field theory technique, or how?
Yes. It's just there are no neutrinos, right? The equilibrium state of neutrino transparent matter is it's protons, neutrons, and electrons, and maybe there's some thermal radiation with some neutrinos being radiated out, but that's all.
So whether you assign chemical threshold to neutrino.
So the neutrinos, in the neutrino transparent regime, the neutrinos do not have a chemical potential. It's not that their chemical potential is zero. They don't have a chemical potential because they're not in equilibrium. They're never in equilibrium. Okay, in the neutrino transparent case, we do not treat neutrinos as being equilibrated. We treat them as some form of radiation that leaves the system.
Okay, but do you have a kind of parameters that how to say interpret these two limiting cases?
Yes, the neutrino mean free path, right? If the neutrino mean free path is bigger than the star, it radiates.
Okay, I see. Thank you very
That's
much.
another transport property that I'm not going to talk about, but you know, there's plenty to talk about here. You're quite correct. Have we answered your question? I'm going to carry on. Okay. All right. So there is critical equilibration. So now I feel justified in going on and exploring some of the physical consequences of there being a critical equilibration of the proton fraction happening in neutron star mergers, at least, and actually, I think also in individual stars under the right conditions. So here we go. We'll have a quick summary of where we're at. Okay. Neutrino trapped matter, the proton fraction relaxes very quickly in microseconds. And this might matter if you were doing a merger simulation with a very short time step, and they actually do make sometimes very short time steps like this. But more obviously, neutrino transparent matter at these single MeV temperatures, the proton fraction is relaxing on the same time scale as the merger dynamics, namely that frequency of density oscillations. So the proton fraction equilibration is participating in the dynamics. You can't neglect it. So what are by the way, in reality, the neutrinos, this gets to the question. They have an energy-dependent mean free path. It's really quite complicated, but we're sticking to these two extreme cases just to get started. So what are the physical consequences of having the relaxation time being comparable to the oscillation period? What are the physical consequences of this? So the main physical consequence is bulk viscosity. So I'm going to describe what bulk viscosity is. Okay, I'm going to describe it in this context, but my description is generic. This will be an explanation of what bulk viscosity is in general. So it arises when you've got a material with some property, and in our case, it's the proton fraction, that takes time to equilibrate. It's a bit slow. And so what happens is if you've got a density oscillation, then, okay, the density is oscillating, and that means conversely, you can think of a fluid element with a fixed number of baryons in, and its volume is oscillating. Those are the same thing. And the oscillation of, in this case, the volume of the fluid element becomes out of phase with the applied pressure. And that means that if you calculate the PDV work, that the force that's doing the oscillation, the work that it does on that fluid element, you'll find that over one cycle, the net work is not zero. It makes a net loss, okay? So it does more work on the fluid element than the fluid element does back on it. So let's just see this in more concrete terms here. So we talked about the fast equilibration limit here, where the fluid element is always going back and forth along the equilibrium line. We talked about the slow equilibration limit, where the fluid element is going back and forth with a constant proton fraction. In both these cases, if you know the density, then you can tell me the proton fraction. It's going back and forth along a line. So if you ask what this fluid element is doing in pressure volume space here, it's just going back and forth along a line. The pressure is a function, remember, is a function of the density and the proton fraction. But if the proton fraction is just a function of the density, then when you compress it, the pressure goes up and the volume goes down. When you uncompress it, the pressure goes down, the volume goes up. It goes back and forth along this line, and the net integral PDV work done on this fluid element is zero, because you do the integral this way along the line, then you do the integral that way along the line, and it adds up to zero. So that's like a classic Hooke's law spring. You squeeze it, you do work on it, then you relax, let it expand, it does work on you, and the work it does on you is the same as the work you did on it, and everyone's happy, right? Now, what if we're in critical equilibration? In critical equilibration, in density proton fraction space, the fluid element is tracing out this loop. And since the pressure is a function of proton fraction as well as density, right? If you change the proton fraction at a given density, in general, you change the pressure. So that means in this fluid element in pressure volume space is also tracing out a loop. Okay, when you compress it, you increase the pressure and decrease the volume. And if you then ease off and let it expand again, the pressure goes down and the volume goes up, but it doesn't go back along the same path that it followed when you were compressing it. And that means the area of this loop here is the net PDV work that you, the force that's imposing this oscillation, you do work on this fluid element when you put it through one of these cycles, because you do more work compressing it than it gives back when you uncompress it. And that's bulk viscosity. Okay, that's what bulk viscosity is. It's the net PDV work that is done on a fluid element when it goes through one cycle of compression and uncompression. And you can see it's going to arise when you have this hysteresis, this delay in equilibration, that the fluid has some component that equilibrates slowly. Not too slowly, we'll see this later. If it equilibrates very slowly, then you're just going back and forth along a line and there's no dissipation. If it equilibrates very quickly, you're going back and forth along a line and there's no dissipation. Critical equilibration is when you see this effect, this bulk viscosity. So let's now look at, so here, straight to the answer, right? What's the bulk viscosity of nuclear matter? Well, here is a calculation. Again, we're always using the same plane here, the density along the bottom, the temperature up the side in MeV. Here is the plot we saw before, where you see how the relaxation rate is getting faster as you increase the temperature. And here is the bulk viscosity with contours. And what you see here is it sort of looks like a mountain, right? Here is a big bulk viscosity here, 10 to the 29 in these interesting astrophysical units that they like to use, grams per centimeter second for bulk viscosity. And here is the 10 to the 28 contour around it. And 10 to the 27 is along the bottom here and going up the side here. So you can see the bulk viscosity is reaching its maximum right around here. And if you make the system hotter, the bulk viscosity goes down. If you make the system colder, the bulk viscosity goes down. There's a certain temperature where the temperature is just right, and the bulk viscosity is its maximum. And what is that temperature? Well, it's exactly the same as the temperature at which the critical equilibration is reached, the temperature at which the proton fraction relaxation rate coincides with the frequency of the applied density oscillation. And this bulk viscosity, it depends on the frequency of the oscillation. So what we see here for the bulk viscosity is this non-monotonic temperature dependence. As you increase the temperature at a given density, the bulk viscosity goes up as the system relaxation rate gets faster until the relaxation rate matches the oscillation you're doing. And then if you push the temperature higher, it's relaxing too quickly. It's very good at staying in equilibrium. It's not doing phase lag anymore. And now the bulk viscosity drops again. So that's one feature of this plot, this non-monotonic dependence of bulk viscosity on temperature. It looks like a resonance because it basically is a resonance. And the other thing you see is still the contours are pretty flat. Temperature is the main driver, in this case, of the dependence of bulk viscosity, the variation in bulk viscosity. When you increase the density, it dies off a little bit, but basically the temperature is telling you what's going to happen. So, okay, that's bulk viscosity. Now, I'm going to say a little bit more about that in a second, but one thing I'm going to admit up front is, you should always ask this question, right? Is this a big number, right? And you look at this, well, it's 10 to the 29, right? That sounds like a big number. But of course, that's to do with your choice of these, Renaissance French units, right? So is 10 to the 29 a big number? It's hard to tell, right? I mean, bulk viscosity sounds physical, but, honestly, looking at this, you can't really tell. So later on, we'll get to something where you have a better sense. We'll use this to get something that's more directly physically interpretable. So don't worry if right now you look at that and go, oh, okay, he says it's at a maximum, but do I care? Because is it big or not? We'll get to that.
Excuse
okay.
me.
Yes.
Can one try to measure the bulk viscosity, say, on the lattice?
I expect you can, yes. Probably, let's think. So the static bulk viscosity would be the zero frequency limit. That's probably measurable, but if you choose the right, yeah, some interesting correlation function in Euclidean time will get you that, I expect. Some Kubo type thing.
But you need the, I think, the real-time correlator in that case, and it is difficult to measure in the on the lattice.
Right. Well, okay. So the thing is, this is the weak interaction. So you kind of don't need to do the lattice, right? What you need the lattice for is the strong interaction sort of dressing of this process. But mainly, it's a weak interaction. This goes to what I'm going to talk about next week, actually. All right, is how does the strong interaction dress weak interactions? And that strong interaction dressing you might want to look at on the lattice. But the weak interaction itself is very perturbative, right? I'm just doing single W exchange here, and there's no reason to go to two Ws because that's going to be heavily suppressed. So my initial thought is hold that until next week when I will talk about strong interaction corrections to these rates. One particular type of strong interaction correction to these rates.
I have related question. That here you show the bulk viscosity, and so I think that you have the Kubo formula so that you can evaluate the bulk viscosity from your theory as you like. So, but is this bulk viscosity extracted from your discussion of this chemical oscillation or kind of the flavor oscillation behavior?
I mean, this was just calculated doing a sort of Fermi's golden rule type calculation of a weak interaction rate.
Oh, I see. So you just evaluate the bulk viscosity from the field theory?
Yes.
Oh, I see.
Right. Exactly. I'm jumping over some of these details because I realize I don't have time to give an entire course on this. Okay, so let me just go on a second. So let me just say something about this resonant thing that I just mentioned. The bulk viscosity is a maximum when the flavor relaxation rate matches the frequency of the applied oscillation. And there's actually a formula for this. The bulk viscosity, this is zeta, the bulk viscosity, in terms of these two quantities, has this form: relaxation rate over relaxation rate squared plus frequency squared. So as you vary the rate, the relaxation rate here along the bottom, which is really varying the temperature, which varies the rate, and look at the bulk viscosity as the y-axis here, it goes up, reaches a maximum, and goes down again. And that's related to the physics that we were talking about before. So if the equilibration is very fast, high temperature, the equilibration is very fast, the system is always in equilibrium, there's no phase lag between the pressure and the density, so you don't get that hysteresis, you don't get any bulk viscosity, so the bulk viscosity tails off to zero at high temperatures, fast relaxation. At low temperatures, down here, where the relaxation is slow, again, the bulk viscosity is small because the system isn't even trying to equilibrate. Basically, we've just got another conserved quantity, proton fraction, or proton number. And so it's just another conserved quantity to keep track of, and there's no phase lag going on. It's this point here where the relaxation rate matches the applied frequency, applied oscillation frequency. That's where you get this maximum in the bulk viscosity, and this formula reflects that. So, okay, let me go on now to something physical, like I promised, a more physical, understandable consequence of this. So let's look at the back reaction that the bulk viscosity exerts on the applied density oscillation that started the whole thing. So this is a damping time. It's different from the proton fraction relaxation time. So now we're looking at this density oscillation, and we're saying, okay, it's got a frequency omega, but also it's going to die away at some rate given by some damping time. And they're different. The relaxation rate is how long it takes a proton to turn into a neutron, basically. That's a microscopic thing. This damping time is how long does it take for a density oscillation to lose a significant amount of energy as a result of bulk viscosity. So let's look at that. How do we calculate this damping time? Okay, well, let's look at the density oscillation. All right, it's carrying energy. So how much energy does a density oscillation carry? Well, it's just a simple harmonic oscillator, right? So it's just the spring constant times the amplitude squared. So in this case, people talk in terms of this thing called the nuclear incompressibility K, which has got some funny normalization factors here, but it's basically the spring constant times the amplitude squared. That's the energy stored in the oscillation. And the other thing we need to answer this question is how quickly is it losing energy due to bulk viscosity? And that we look at the PDV work, right? And the bulk viscosity tells us how much PDV work this oscillation is losing in every cycle. And the rate at which it's losing energy is given by the bulk viscosity times some factors of frequency squared, and then it goes like the amplitude squared as well. So if we want to know the damping time, what do? Well, we take how much energy we have and divide by how quickly we're losing energy, and that tells you the damping time. Okay, well, that tells you the time scale on which the oscillation will lose a significant fraction of its energy. So the damping time is how much energy the oscillation has stored in it, divided by how quickly is that energy being taken away by bulk viscosity. You divide these two things, the amplitude cancels out because it's linear response where amplitudes always cancel out. And basically, apart from some of these definitional factors, it's basically the incompressibility divided by the bulk viscosity, right? So it's saying, you know, if the incompressibility is big, it stores a lot of energy, so it doesn't care if there's bulk viscosity. It takes ages for the oscillation to damp. And conversely, if the bulk viscosity is very big, then it damps out very quickly. Okay, so the damping time for an oscillation depends on the incompressibility, how much energy the oscillation stores, and the bulk viscosity, how quickly that energy is being taken away. So now we have another quantity that we can compare with the timescales of mergers. And this time, we know what's going to count as big and small, right? It's not, no, it's like, is 10 to the 29 a big number? We don't have to worry about that. If oscillations get damped in 10, 20 milliseconds, that's the timescale of a merger. Then it's an important aspect of the physics. If this damping time is 10 seconds, then it's not important in mergers, right? So this is something where we can have a direct physical sense of, is the physics relevant or not? So let's go straight to the answer again. Here is our classic plot, density along the bottom, temperature up the side, and now we're plotting this damping time, compressibility divided by bulk viscosity, and these are contours. This time it's fastest, the damping is most effective at the temperature here, the 5 MeV temperature where the bulk viscosity is biggest. That's not a surprise. The question is, what's the time scale? And the answer is, in this case, 25 milliseconds or 50 milliseconds, 100 milliseconds. These are time scales that are relevant to a merger. So we conclude here that we have physics that can't be neglected. All right, if there's nuclear matter in this density range, which there certainly is, a few times saturation density, and this temperature range, sort of single-digit MeV, and we're assuming neutrino transparent, which is not a bad assumption at these temperatures, then those regions will experience significant damping of those density oscillations as a result of the bulk viscosity, which is as a result of the relaxation of the proton fraction. So there are some other features here, but basically we're saying damping of a 1 kilohertz density oscillation occurs on the same time scale as the merger. So just to sort of recap the whole sort of pipeline here, we started off calculating the rate at which protons can turn into neutrons. At what rate does the proton fraction equilibrate? These are all in the same density temperature plane, and found the equilibration gets faster as the temperature goes up. Then we calculated the bulk viscosity, which is a mountain here with its maximum when the equilibration is critical, when it matches, the equilibration rate matches the density oscillation frequency. And then we turned that into a damping time for the density oscillation and found that it comes out in the interesting time range at 5 MeV-ish temperatures. Okay, in case you're worried about, I assumed an equation of state and, you know, does it depend on that? Here is the damping time plot for two different equations of state, and it doesn't look that different. This is the IUF, this is the QMC RMF3. Both do a 1 kilohertz density oscillation. In this case, it damps a bit faster, 25 milliseconds. In this case, it damps a bit slower, 60 milliseconds. But it's short enough to be relevant for mergers, especially at these sort of 2 to 3 times saturation density range. By the way, why does the damping time get longer when you go up to higher density? That's because the incompressibility goes up, the matter gets stiffer, so the oscillations store more energy. So even though the bulk viscosity is quite big out here at this high density 5 MeV temperature range, at that density, the nuclear matter is stiff and carries a lot of energy, so it takes a long time for the bulk viscosity to suck significant energy out of a density oscillation. That's why these contours are looking a bit more circular for the damping time than they did for the bulk viscosity. Okay, so I talked about the neutrino transparent regime. The neutrino trap regime, I'm just going to very quickly say here, as you'd expect, we saw the relaxation is much faster. So this gamma on the bottom is getting bigger and making the bulk viscosity smaller. Also, this susceptibility in front is smaller. So here's a plot as a function of temperature now of the bulk viscosity, where they switched from neutrino transparent mode at below 5 MeV to neutrino trapped results above 10 MeV with a gray area in between. And you see the bulk viscosity drops quite a bit when you get to the neutrino trapped regime. And that's because it relaxes much faster, stays in equilibrium, doesn't get so much phase lag, all those sorts of reasons. So, okay, I think now I can get to my last 2 slides in good time for the end of the talk. So the summary is neutron star mergers are interesting because they probe not only a range of temperatures that we don't generally see in single neutron stars or, or heavy ion collisions. They don't probe that density temperature range. Also, neutron star mergers probe the dynamical response. They've got a time scale, this 1 to 10 millisecond time scale. So what happens in the merger depends on dynamical properties, static properties too. The equation of state is a static property, but my whole point here is dynamical properties out of equilibrium, relaxation to equilibrium, whatever you want to call it. Those sorts of properties are also important because the merger is a highly dynamic process. We saw that in neutrino transparent matter, at these sort of single-digit MeV temperatures, you get proton fraction relaxing on the time scale of the mergers, and the resultant bulk viscosity is damping density oscillations in this 20 to 100 millisecond time scale. So, okay, what do we do next? Well, I was sort of stuck with these 2 regimes where you can easily do calculations, the neutrino transparent regime and the neutrino trapped regime. What you'd like to do, and I have a student working on this at the moment, is do these sort of equilibration rates, these basically neutrino absorption and emission processes for arbitrary neutrino distributions. And there are people calculating these, doing Monte Carlo simulations of neutron star mergers where they simulate the energy distribution of the neutrinos in fluid elements, as well as the static properties like density and temperature. So we're working with one of those people, Francois Foucault, on that. I only talked about neutron, proton, electron matter. You can also talk about this sort of process, flavor equilibration, in other forms of matter. You can introduce hyperons. My former postdoc, Alex Haber, studied that and found that with hyperons around, you tend to get rather fast relaxation, but that might be relevant at low temperatures. You could also look at other phases, pion condensed phases, nuclear pasta phases, quark matter phases. There are people who've looked at this recently as well. So I talked about the damping of density oscillations, but that's not the only manifestation of flavor equilibration. That damping, where did the energy go? Okay, the energy went into heat and the emission of neutrinos. So you could also look at those effects of this bulk viscous damping, that it heats the medium or it may lead to enhanced neutrino emission. So I only talked about flavor equilibration, but I mentioned that there are other ways in which the system can be driven out of equilibrium and might try to return to equilibrium that might have their own interesting phenomenology. So thermal conductivity and shear viscosity, you can do some very rough estimates, and these may become significant, particularly in the neutrino trapped regime, because the trapped neutrinos with a long mean free path will tend to dominate transport. The guy with the longest mean free path tends to dominate transport. So in that case, the neutrinos would actually be the main contributor. And so, you know, particularly if there are gradients on a relatively fine distance scale, which apparently there are. Every time the merger simulation people tighten up their grids, they start seeing more structure at the new scale that they've revealed. So there may well be things like turbulence going on, in which case there may be short scale gradients, and thermal conductivity and shear viscosity may be important, driven by neutrinos. And finally, I want to say, you can also, while we're going beyond things, you can go beyond the standard model, and you can look at things like axions. And there are various examples of this, but I'm just going to show one as a sort of coda or postscript here. And this is some work done by my former grad student, Stephen Harris, in collaboration with these other beyond standard model phenomenologists. And he looked at the cooling by axion emission in a merger. Here's the temperature, the hottest temperatures you get in mergers, tens of MeV. Here's the coupling of his axion-like particle. Now, supernova 1987A puts a limit, so people think that the coupling has to be below this blue dashed line here. But even if you include that constraint, you find that at the highest temperatures here, a hot region would emit enough neutrinos to cool to half its original temperature in about 10 milliseconds, if the coupling was at the highest level you're allowed. So, you know, axions and axion-like particles are kind of a bit like neutrinos. They're very weakly coupled things, but sometimes the weakly coupled things can be the most important things because they have a long mean free path and they can radiate. So if you're clever in looking for your phenomenology, you may be able to find signatures even of beyond standard model physics in the story of a neutron star merger. Okay, so I'll go back to that and say that's the end, and thank you.
Mark, for like perfect timing. And so is there any question from the room? Yes.
So I'm also interested in the third point. So what carries carry away the energy? So
Right.
neutrino or
So it's some combination of heating and neutrino emission.
heating of fat?
Well, so the apart from the neutrinos, the rest is in thermal equilibrium.
Yeah.
It's Fermi Dirac. So it's just putting heat into the neutron gas, the proton gas, the electron gas.
Goes up.
The temperature goes up. Yeah.
So you include that effect in.
Well, no, we're just calculating the PDV work, but there's some. It's a little complicated because these weak interactions that establish equilibrium also emit neutrinos, and the neutrinos carry energy. So if the neutrinos are radiating away, then it's not quite clear how much goes into heat and how much goes into radiating neutrinos. And we're not. There's been some work on this, not by us, and it's not entirely clear, I would say.
In principle, you can estimate
Yes.
how much energy.
In principle, you should be able to do that. Yes.
Very interesting.
Yes. Yes.
I have a question. So you mainly, you mainly discuss about the frequency of the density oscillation, but what about this amplitude? So in the like first slides, like you showed like, you know, the amplitude is very the density oscillation is large like initially, but it somehow damps like quite, fast.
So yeah, so the calculations I described were in linear response, where the amplitude cancels out, because that's the straightforward thing to do. And if there's interesting stuff in linear response, then there's interesting stuff, right?
Yes.
So that was the conclusion I was trying to make. It is true, though, as you said, that in the first milliseconds, it's clearly beyond linear response. And then you'd be calculating what's called the suprathermal bulk viscosity, where you take into account the fact that you've pushed the system far out of equilibrium. Luckily, in the case of flavor, it's just one parameter that's out of equilibrium. It's one chemical potential, because everything except the neutrinos is thermally equilibrated. So you don't have to worry about deviations from Fermi Dirac. It's all Fermi Diracs. It's just that the chemical potentials are out of whack. So you just have to track this one chemical potential. And if this chemical potential is far out of whack, then that's suprathermal nonlinear bulk viscosity, but you can still calculate it because the rest of it is all thermally equilibrated. So people have done these calculations. We've done them, other people have done them for suprathermal bulk viscosity, and it is some nonlinear effect, which you can't easily capture in a single number.
see.
But yes, there is enhanced, and it becomes less dependent on the temperature. It sort of exchanges temperature dependence for amplitude dependence.
So is the dissipation larger for that, or is it like?
Well, it's yes, because it switches. Yes, the answer basically is yes, because you're turning temperature factors into amplitude factors, and once the amplitude is bigger than the temperature, how you compare those, I've glossed over. But once the amplitude is in some sense bigger than the temperature, the amplitude dominates.
I see. Interesting.
Do you want to look at the
Yeah, I think there's
got here?
two questions in chat. Do you want to speak up, or shall I read it out? Like first.
Hello.
Yes.
I can try to speak up perhaps. So I was wondering if you would expect to see the indications of those pulsations and possibly the relaxation itself also in the electromagnetic signals from the mergers, or are they hidden by other processes like jet formation, for instance, and so on and so forth? Like, how do we search for them practically?
Yeah. So here I'm going to sort of take cover by saying there's a pipeline here, right? Microphysics goes in at one end, goes into the merger simulation. The merger simulation runs and produces a prediction of what we're going to see, and those predictions are then compared with observations. So my role is at that initial end of the pipeline, supplying microscopic properties of the material. Now, the merger, the reason we need to do a simulation is because a merger is a highly nonlinear, unpredictable process where it's very difficult to say, just from changing the ingredients that go in, what effect is that going to have on the behavior and the observable signatures? It's hard enough with the equation of state, right? To say, if I change the equation of state, how is that going to change the spectrum of gravitational wave emission? How is that going to change nuclear synthesis? How is that going to change the kilonova? The reason we need to do simulations is it's not really possible, I don't think, to intuitively connect the inputs to the outputs. So my honest answer is, I don't know. I just have to supply data to the merger simulation people so that they can answer that question. Sorry.
Thank you.
Sorry to cop out on this. I realize it's an interesting question. It's just that we would need to do the whole pipeline.
So the next question is by Tomoya Hayata-san. So do you want to speak up, or?
Oh, yes. It's about breakdown? Yeah, okay.
Can you hear me?
Sure. Yeah. Yes.
So can you distinguish whether the dissipation is relevant or not from observational data?
Yeah, so I mean, in some ways, I'm going to answer that question the same way as the last question. I can't immediately tell you that the sort of dissipation I'm describing, or other kinds of dissipation, thermal conductivity or shear viscosity, I can't immediately tell you that they're going to have some clear individual signature. But my point is, they are relevant to the physics, okay? They are operating, like the damping of the density oscillations is operating on the relevant time scale. So if you don't include this relevant physics, then any inference you do from your data is going to have a systematic error or a bias in it, right? So even if what you're trying to do is just infer the equation of state, you're not going to get you're going to get a biased estimate of the equation of state if you've left out some physics that was actually playing a role. So I don't think we can trace through individual ingredients to specific final signatures generally. We can't say, oh, shear viscosity is going to do this to the gravitational waves, bulk viscosity, damping of density oscillations is going to do this to the ring down. It's not easy to make those connections through the complicated dynamics of the merger. All I can say is, if the physics is there and operating on the same time scale, you mustn't neglect it.
Oh, I see. Thank you.
Okay, so is there any other questions? Yes.
You show the equation of state dependence on the damping time, and maybe the difference of the equation of state plays a role on maybe compressibility or stiffness. But I want to ask the role of the effective mass. So is the effective mass important in your analysis or not? Yeah, it may show the density dependence possibly.
Right. So the equation of state, the strong interaction properties come in various ways, as you said. One of them is that incompressibility that came into the calculation of the damping time, but also even when we're calculating at the very beginning, calculating that proton fraction relaxation rate, that rate depends on the energy momentum relations, dispersion relations of the in medium proton and neutron. And as you said, the in medium proton and neutron have effective masses that may be very different from their vacuum masses. And so that's one of the ingredients in our calculation. And absolutely, yes. So we use relativistic mean field theories, which predict effective masses and energy shifts. They predict a quite different dispersion relation for the in medium neutron and proton. And we use those in our calculation, and they affect the rate. So that's another reason why different equations of state, or different theories, microscopic theories really, which lead to different equations of state, are going to give you slightly different answers. So yes, that's important.
Okay, so is there any other questions from Zoom audience? So this is last call for questions. I see none. So then we would like to close this today's seminar. So thank you very much.
We'll see you next week, maybe.
Yeah, maybe. There'll be another lecture on Tuesdays, right?
Yeah, same day,
Yeah.
same time, I believe.
Yes.